So now that I've broached the subject of synchronizers, let's begin our discussion of synchronizers. And as I mentioned, synchronizers will start to play an increasing role in part B of all of our forthcoming assignments. And so we'll start first by talking about these mechanisms here. So what we're going to do first is I'm going to explain to you the purpose of Java synchronizers. What problem are they trying to solve? And the typical thing you use with the synchronizer, it's an object of some form or another, and you use it to control the flow of cooperating threads based on the state of the synchronizer. And a great example, I love, you'll find if you haven't figured it out already, I love human-known examples of things, because I personally understand technical things better sometimes by seeing the analogy or the metaphor, and that draws me into the actual technology a lot better than just being given a set of APIs and semantics. So a classic example, some of you may come from countries that have trains. The US doesn't have a whole lot of trains anymore, but they used to. There were a lot of accidents when we had lots of trains. And a lot of countries still do have trains. And one of the things you often have in countries with trains is the need to have multiple trains share a single track. Anybody who's ever been to Washington, D.C. or New York or Boston, they have subways or metro systems there. And every once in a while, something will go awry. One of the tracks will have a problem, and then they'll be doing single tracking. And that just means that multiple trains have to share one track. We'll talk about an important synchronization problem, right? Those of you who live in countries with a lot of trains know that from time to time, there are horrific train accidents because people failed to obey the synchronization flags and signals. And one of the classic signals you would find is something that's called a semaphore. We'll talk more about semaphores later. Semaphore comes from various places, but not least which is trains. And there you basically have these flags that say, stop, do not enter the shared track because there's a train on it. And once the other train leaves the track, clear, you can go on the track. So the idea is either the track is clear and you can go on it, or there's something on the track, you've got to stop. So that's an example of a simple coordination mechanism. And there's lots more that we'll talk about. The Java synchronizers are designed to ensure that threads obey certain properties. We want these threads to follow the rules. And the whole model works in Java because people voluntarily follow the rules. If you don't follow the rules, in many cases, in some cases you have to follow the rules because of the way the program is written. But there are other cases where you're writing the program, and if you don't follow the rules, nobody stops you. It's just that chaos and insanity ensues when you run your program. And you will get that experience firsthand with assignment 1B. So let's talk about some of the things that can go wrong. What are some of the properties that can be violated? Probably the most important property of all is not to corrupt shared mutable data, sometimes called shared mutable state. And if you want to amuse yourself, you can read this link, which has a title of something like, Why Shared Mutable State is the Root of All Evil. And it's actually kind of funny because if you look at the world as a whole, how many conflicts in the world result from trying to share stuff, right? People say, that's mine, no, that's mine. They fight over it, right? So in our little virtual world of computing, we have the same issues. You have the same issues on the highway, which is why when I talk about this problem, I always show this little picture. Two cars try to share the same state, right? The same piece of the road. What happens? Collisions, corruption, destruction. And here it's pretty clear that's happening. In computer systems, it's not always so clear. So let's take a look at this problem. This is, by the way, this is often called a race condition. We'll talk about that later. So let's take a little example. This code is something that you could easily implement, and it's called Nonatomic Ops. I should really have said buggy Nonatomic Ops. And what we're going to do is we're going to define a counter called mCounter using a limited form of Hungarian notation called the app form of Hungarian notation as opposed to the system form of Hungarian notation. And this counter starts with the value 0. And then we're going to have two methods, one method called increment, one method called decrement. Method increment will run in thread T1. Method decrement will run in thread T2. And this guy will increment, and this guy will decrement. And the question is, let's say for sake of argument, if we run this, let's say we run this for 1,000 times in 2 threads of control, what will the results of M counter be when both programs finish, or when both threads finish? We haven't the faintest idea. And that's because they're incrementing this shared counter, but they're not doing it in a way that is properly synchronized. So going back to the discussion of the caches we talked about before, it could very well turn out that thread 1 caches the results of M counter, and it does changes in one thread, and this other thread is running in a different, this other method's running in a different thread, and it's decrementing a cached version. And so they might be incrementing and decrementing completely distinct cached versions of M counter. And even if we were to try to solve that by making M counter be something called a volatile, we'll talk about volatile later, we'd still be screwed, and we'll talk about why we'd be screwed later. But the basic reason is that these are not incrementing and decrementing by 1 is not an atomic operation, number 1. And number 2, there's no guarantee these things are even cached in the same location because they're in 2 different threads. They could be running in 2 different processor caches. So we haven't the faintest idea what the results will be, and they'll be wrong, whatever they are. They're not what you expect. Now, it turns out that there's some really trivial ways to solve this with Java, and this uses Java 1.0 features, namely synchronized methods. And believe me, there's like 17 different ways to do this, but this is probably the most obvious way to do it. You simply mark the increment and decrement method with the synchronized keyword, and what that means is that this method can only run, this method will have exclusive access to the object of the atomic ops class. Now, this particular approach is somewhat wonky because either this will run first or that'll run first. They won't ever overlap, but it'll certainly end up with a deterministic result. And this will, in fact, make sure that only one thread at a time is either incrementing or decrementing M counter, and then you'll end up with a sensible result. It won't end up being corrupted. There won't be race conditions. So you can either have synchronized methods or synchronized statements. And those are easy ways of doing this stuff. We'll talk about lots of other ways. These are easy, they're not always the best way to do it. Yes, sir? Great question. So I will cover this in excruciating detail later, but let me give you the Cliff Notes version right now. What synchronized does is 2 things. First, it ensures there's mutually exclusive access to the object for which increment and decrement are being called. And what that means is that only one thread at a time can be inside of this block incrementing or decrementing that counter. And the analogy to have in your mind for this, and you'll see a picture of this, you've probably seen a picture already, is an airplane restroom with the little sign occupied and vacant. So if you've ever flown in an airplane, you've undoubtedly had to use the restroom, especially if you've flown on a long flight. And you know the protocol, you walk up to the restroom, ideally not using the front restroom because they don't want you to queue, but you go to the back restroom in a plane, and what's the rule? When you walk up to the restroom, when it says vacant, what can you do? You can open the door, go in, shut the door, and you push the latch shut. What happens when you push the latch shut? What does it say? Occupied, right? And then you do your thing. We'll ignore that part. Then when you're done, you, the person who's in the critical section where the goal is to have one thread at a time, one being at a time, one person at a time, you slide the latch back, open the door, walk out, shut the door, and now what does the latch say? Vacant. And what's the rule? If you show up at the door and it says occupied, what are you supposed to do? You have 2 choices, right? You either wait or you say, oh, it's locked, I'm going to go back to my seat, right? So the rule is, if you go to the front of the plane, then when it says locked, you're supposed to go back to your seat. If you're in the back of the plane, you can queue. When the latch changes from occupied to vacant and the person leaves, what happens next? If there's another person in line, they get to go in. So if that's a critical section, the restroom's the critical section. It's kind of like the stuff that's after synchronized curly brace, but before the closed curly brace. So what you're saying is one thread, one person, one being, whatever, at a time can be in that critical section. And anybody else who wants to get in there has to block and wait. Now, one of the things you'll see with this particular approach is in an airplane, what's the typical protocol? If there's a line of people waiting for the restroom and someone leaves, who goes next? Typically the next person in line, unless there's a screaming kid who needs to go to the restroom, and then they get boosted in their priority and they go next, right? But the point is that we have some options, right? One option is strictly first in, first out, right? That's sort of the fair way to do it. There are other situations where the screaming kid gets to go next, right? So we'll talk later about that when we get farther into the course. That's not important right now. Yeah? Oh, great question. Within a synchronized method, then the synchronization block is from the open curly brace to the closed curly brace. Yes. So the one thing it does, you asked what happens. So the first thing that synchronized does is it says, let's make sure that only one thing at a time is in this critical section. The second thing that it does, and this is really important, is when you leave the critical section, the system automatically flushes the cache of the thread that was running at that point and takes the memory that was in that cache and pushes it out so that the next thread that comes along who wants to get in that critical section will read the updated value that just finished over here. So let's say, for sake of argument, this thread gets the synchronized block, the statement, it increments the counter atomically because there's nobody else doing it at that time, because the semantics of synchronized mean one at a time. When the closed curly brace is hit, this thing is flushed back to main memory such that when this guy comes along and goes to run in its block in a different thread, it'll read the latest value atomically and consistently. So there's two things, guaranteeing mutual exclusion and flushing the caches. And those are really two separate behaviors, and we'll talk about that more later, but the synchronized method combines both of them. There's other stuff that lets you do other things. Okay. So that's one thing. Don't corrupt shared mutable state, shared mutable data. That's what's typically called mutual exclusion. And the other thing is to make sure that operations occur in the right order, at the right time, and under the right conditions. This is what's typically known as coordination. So we've got mutual exclusion, which is this guy, and coordination. We'll talk about this a lot more. So let's take a look at a simple example. We have a couple minutes before the quiz. So one way of using synchronizers, in addition to ensuring mutual exclusion, is to ensure things run in the right order, at the right time, and under the right conditions. So we'll talk about a fun little program I call the ping pong example, where we have two threads, a ping thread and a pong thread, and they're supposed to take turns printing ping, pong, ping, pong. And what you'd like them to do is to have them alternate. So you print ping, pong, ping, pong. If you don't coordinate these methods properly, look what can happen. You might, do ping, 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 pong, 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 pong. That's not right. So this would be the wrong way to do it. So I actually have a little piece of an example called ping pong wrong, which was mostly there just because I wanted to have the clever rhyme scheme. So ping pong wrong shows how not to coordinate two threads. If you use a synchronizer correctly, in this case, say a semaphore or a condition object, which we will talk about in more detail, then you can coordinate these threads so that they run under the right condition, in the right order, at the right time. And then you'll get the right result. Ping pong, ping pong, ping pong, and so on and so forth. So we'll look at that a little bit later when we get talking about things like semaphores. The last thing I want to do is just kind of talk about how pervasive synchronizers are. There are synchronizers all over the place in modern platforms, Java included. Some things are in the Java execution environment. They're actually built into the Java virtual machine or the Android runtime. And these include things like volatile variables and built-in monitor objects. So those things are really baked in at a very low level, written in C, typically. And then there's other synchronizers and a vast number of other synchronizers that are provided in the Java class library in the form of things like locks and barrier synchronizers and coordination mechanisms and atomics and so on. And so those exist up the stack a little bit. We're going to focus primarily on these, but we will also talk about these things as well. There just aren't as many of them to talk about. There's a legion of these things to talk about. And by the time the class is done, you'll see that we end up spending about an equal amount of time covering variants of threading and variants of synchronization. And all the assignments will give you practice with different threading mechanisms doing the beans, and you'll also get a chance to play around with synchronization doing the Palantir manager, which will be coming up soon. So by the time you're done, you'll get a chance to play around with about a dozen different techniques. Synchronization is in many ways more complicated than threading because you have to coordinate the interactions of a bunch of different entities running concurrently. Remember, the whole point about concurrency is to try to do many things at once that have to be coordinated, whereas with parallelism, you want to run a lot of things that are independent of each other. So this is a good metaphor, I think, about the trickiness of coordination of many things running independently. Does anybody want to take a guess as where this might be? Yeah. I've actually been to Bangalore and Hyderabad, and it looks pretty much like this. Most of the time. It's pretty amazing. It's actually even more fun because you would think that there would just be an enormous number of fender bender accidents, but somehow the drivers seem to have like this ESP that lets them get this close to each other without running into the other car. It's really phenomenal. It's completely terrifying, by the way, if you're not from there, but it's really fun to experience it. The parallelism frameworks that we'll talk about next semester sidestep all this stuff by using divide and conquer approaches. So they don't share stuff, but concurrency does. Okay, so that's the end of that discussion.